Here I want to derive an important corollary of the divergence theorem, which tells us that if we integrate over a closed surface a vector field f and we take the dot product with the unit normal to the surface, integrate over ds, this is equal to the integral of the divergence of the vector field f over the volume. Now we will choose f to be a function of this kind. It will be a scalar function g multiplied by a constant vector field. So c will be a constant, whereas g will be a function. But g will be a scalar function and c is a vector field, even if it is constant. And if we substitute this expression there in our divergence theorem, we get c. We can pull it out of the integral because it is a constant vector field. Dot product with the integral over the surface of g and ds, and this is equal to, now we have integral, we have the divergence of gc dv, written like this. Now c is a constant, as I said, so we can rewrite this as sum over I of the derivative with respect to the ith component of gci, and ci is a constant, so we can rewrite this as sum over I dig ci, which is equal to the gradient of g, and then we take the dot product with c like this, and therefore we can rewrite this as c dot product integral gradient g dv. But now, since c is an arbitrary field, even if it is constant, it is arbitrary, therefore we can rewrite the identity like this. We have integral over the closed surface g and ds equal to integral gradient g dv, like this. And this is an important identity. For example, Einstein used this identity in his paper on the molecular dimensions. It was his PhD dissertation in which he solved Navier-Stokes equations and which allowed him to find some important equations to estimate molecular dimensions.